Hi, welcome back to Kirsty's virtual classroom. Today we're talking about the Peninsular Ranges in Southern California. The Peninsular Ranges are landlocked by the Transverse Ranges and the Colorado Desert cut off here. And then they do interact with the Pacific Ocean. So we're in Southern California down here looking at these ranges here. Okay, so like the transverse ranges, the peninsular ranges are composed of multiple mountain ranges. These include the Santa Anas, Santa Rosa, Palomar, San Diego, Agua Tibia, and the San Jacinto. So if we take a look at some of those mountain ranges, here they are. So to the north we have the San Timoteo, the San Jacinto, the Santa Rosa, and then on the eastern portion, we see Anza Uplands, the Borrego Valley. And then here we have our faults. It's part of the San Andreas Fault System. Then we see the San Felipe Hills over here to the southeast. On the western portion, we have Agua Tibia. And then we have another strand of the San Andreas Fault System. We'll talk more in depth about what these specific faults are. And then we have Laguna to the south, and then Santa Margarita and Santa Ana to the north. All right, so the rocks in the area are mostly plutonic. So the region is underlain by these plutonic rocks that are from magmas that generated during the subduction of the Farallon Plate. If you remember in the previous lecture, we talked about the subduction of the Farallon Plate and it disappearing millions of years ago. And then we see now the plate boundary interaction between the North American plate and the Pacific plate. So around 140 to 90 million years ago is when we saw the disappearance of the Farallon plate. So subduction is not currently occurring. So the geology of the Peninsular Ranges shows extensive masses of granitic rocks, so similar to the Sierra Nevada batholith, which we haven't fully talked about yet, but we've kind of alluded to it a little bit. So the Sierra Nevada batholith is obviously part of the Sierra Nevada, and these Peninsular Ranges batholith are similar, and we're kind of going to talk about the differences between the different rocks. So over this long period of time, we have extensive masses of granitic rocks accumulating at depth to form this Southern California batholith. And remember, a batholith is just a collection of a bunch of different plutons. So remember, plutons form underground, so there's no volcanic eruptions or anything occurring. The magma solidifies underground and then is exhumed by erosion, weathering, and tectonics. Intense heat associated with these plutonic magmas has metamorphosed some of the older sedimentary rocks in which the intruding magma intruded into, basically. So we do see some lower grade metamorphic rocks, and then we have some metasediments that are now preserved in the Peninsular Ranges as marbles, slates, schists, quartzites, and gneisses. So all of these rocks are actually present in the Peninsular Ranges. All right, so the trend appears to be similar to the Coast Ranges. So we have that northwest, southeast trending, but their rocks are more closely resemble the Sierra Nevada than the Coast Ranges rocks. So this is kind of an interesting note. The two prominent faults in the area are the San Jacinto Fault and the Elsinore Fault. The Elsinore Fault is the major fault that parallels the San Andreas Fault System. Right, so those are the two that were outlined in that previous map that I showed you. But here's the Elsinore Fault to the west and the San Jacinto Fault to the east of the Peninsular Ranges. So the Elsinore Fault is in this photo. It enters on the left along the base of the hillside and disappears in the distance in the center of the photo. So this is approximately where the Elsinore Fault lies. This fault extends to the north through Lake Elsinore, to near Whittier and extends to the south towards the Mexican border. So it goes pretty far as we look back at this image here. So it extends up to Elsinore Lake, and then it goes all the way down to the Mexico border. And there's the fault there for you. So here's the Elsinore Fault at the base of these mountains, which is controlling the uplift of those mountains. And then it kind of trickles and disappears somewhere in the middle here. The San Jacinto Fault is also part of the San Andreas Fault System. The straightness, continuity, and high seismicity of the San Jacinto Fault Zone suggests that it may currently be the most important member of the system. So during Module 5, a lot of you actually noticed that this fault had some significance to movement in the area, and a lot of you pointed that out and wanted to talk about this fault. So here we are talking about it again. So can you see in this photo where the San Jacinto Fault might be? I'll give you a second. Okay, so right here at the base of these mountains, we can see a clear, distinct line. There's a difference between this low-lying area and these mountains. They're not very high. They're not like Sierra Nevada high mountain ranges, but they have a pretty significant delineation between this valley and these mountains or hills. So if we take a look at the earthquakes kind of in the area, remember we're down here near San Diego, near the Mexico border. The earthquakes in the area are typically between a 5 and a 7, with an average of about a 6. So towards the north, we have some ruptures in 1923, which was a 6.3, and to the south, we see a rupture in 1987 of a magnitude 6.6, and varying degrees in between along the San Jacinto Fault. So in 2010, we did see something we called, or we named, the Mexicali earthquake because it occurred near Mexicali, Baja California. So if we kind of look at earthquakes during that time, so this is April 6th, 2010, you can kind of see the different earthquakes that happened in the last hour, last day, last week, relevant to that date. And they are sized by magnitude. So you can see some of these really large last week size almost 7 magnitude. So it was a 7.2 magnitude. And there along the San Jacinto Fault, we see a lot of additional earthquakes that occurred after the bigger earthquake. Here's another look at that earthquake. So here we have elevations. So that's what the gray shaded areas are. So the highest elevation is here. And you can see on either side of these faults are the higher elevation areas. And in between, we kind of see a drop down zone, which we also see some rotation in as well. So the San Andreas Fault is the eastern portion of this system down here in the southern portion, and it is pulling southeast, and the San Jacinto Fault is pulling this area to the northwest. So the San Jacinto Fault is part of the Pacific Plate, and this part of the San Andreas Fault is part of the North American Plate here. And down here we also have an additional fault called the Laguna Salada Fault. And in the middle, or sorry, not in the middle, near these faults we see an uplifted block. So that's what's generating all of the different mountains that we see in the Peninsular Ranges. So the province is a large block that is uplifted abruptly along the eastern edge and tilted westward, much like the Sierra Nevada. And the highest point of the San Jacinto Peak is above Palm Springs. So here is Mount San Jacinto. Elevation is at 10,834 feet above sea level. This is where we do see snow in these ranges. Here's the benchmark for it. And some think that The Peninsular Ranges were once part of the Sierra Nevada magmatic system. They are geochemically similar, but they are not identical. So if we look at some of the rocks from the Peninsular Ranges versus the Sierra Nevada, they do look kind of similar. They're both granite for sure, but their chemistry is not identical. And that's to say that, it's like identical twins, right? They're not identical, but they could be fraternal. So they can be from the same processes, from the same subduction of the Farallon plate, but they might not be part of the same batholith. So here's a look at their geochemistry. So the western portion, which would be the Peninsular Ranges, versus the eastern portion, which would be the Sierra Nevada, excuse me. So we can kind of look at some of these similarities. Some are different, just depending on what we're looking at. The silica is one of the most important things to look at, the silicon oxide, because this is the primary component in the quartz crystals. So we would look at quartz crystals and kind of decide if they look similar to quartz crystals in Peninsular Ranges versus Sierra Nevada. And then we can look at the magnesium, the aluminum, different, amounts of things and compare them and see if they're similar. So you can see similar trends in some of these, and others, they're vastly different. So I'll let you decide. Do you think the Peninsular Ranges granite are the same as the Sierra Nevada granite? I will catch you guys in the next one, and have a good day. Bye.